Hi, my name is Byungsoo Ko from Naver. I'm going to talk about our paper, Learning with Memory-Based Virtual Classes for the Metric Learning. Metric learning problem requires decent generalization performance because there is class difference between training and test dataset. So our method tries to improve generalization performance in the metric learning by using memory-based virtual classes. This is motivation of our proposed method member. When we trained the learning model, each model had a different weight in each training step because there was a series of weight updates, so they were basically perceived as different models. Then different embedding space will be obtained for classes A, B, and C at different training steps. By taking advantage of this feature, we will let the model save embeddings and proxies of the prior steps in the memory queue, and the model will use the saved embeddings and proxies as if they were new virtual classes. The use of virtual classes can alleviate strong concentration on actual classes of training data, which will result in improved generalization. Also, member can be applied to various proxy-based laws. Member has an advantage over the original method because it can train the model with a lot more classes and instances, which work as augmented information using additional virtual classes. Also, the learning difficulty will be increased gradually using curriculum learning method to enhance optimization stability and final performance. We have gradually added virtual classes to increase the difficulty level step by step. To give you a more perspective on how member works, this is the process of conventional loss computation when member is not used. Mini-batch goes into convolutional network, forms embeddings, and then learn to consider the similarity between embeddings and class weight. This proceeds within the actual embeddings and class weight, and here, class weight serves as a proxy. When member is applied, virtual embedding and class weight are added in training progress, as you can see here. Virtual embeddings and class weights are from the memory queue, which save every step's embeddings and class weight. Selecting previous embeddings and class weights to use virtual classes are depending on margin M, which is in between selected steps. And we use N as number of steps to use. The reason we put margin between steps is that the disparity between embeddings of closed steps is small, so the training difficulty can be too high. As a result, we can control the training difficulty of member by adequately adjusting margin M and number N of the previous steps. We visualize embedding space through t-SNE visualization during training. Pink dots are the embedding in the current step. Image A and B are until 50th epoch without any virtual class. In image C, D, and E, classes of the previous step have been gradually added as virtual classes. Given the model more time to learn, then you will get embedding space with actual and virtual classes evenly distributed just like image F. This means member alleviates a strong focus on the training classes and helps to obtain generalized embedding spaces. Lastly, we've tested whether member can flexibly adapt to various types of losses and data. You can see a table here where member was applied to various loss functions and 3 benchmark datasets, and it showed a minimum of 1% and a maximum of 5% performance improvement. Thank you for listening. More information about this project can be found in the archive and GitHub link.